Okay, let's make a start. So you're all still alive, that's good. Are you looking forward to the weekend? Yeah? Oh. Okay. Linda informs me that it's National Carousel Day today. Yeah. Apparently it's relevant, so Linda will inform you how later on. Right, so we've got two talks this morning. We've got another session on impacts. And the first talk is going to be by Rob Wilby, who's Professor of Hydroclimatic Modelling at Loughborough University. I've known Rob for a really, really long time now, since he was the first person I ever wrote to, and I mean actually wrote rather than emailed, when I, exactly, it was a really long time ago. I wrote him a letter when I first started my PhD to ask him about his downscaling work, and he replied to me. It was amazing. So, so I've always been really impressed by Rob's work. Rob's really a jack of all trades as well, a bit like myself. A downscaler, looks at hydrological modelling, water resources modelling, and also more recently looking a lot at adaptation. So I'm going to let him tell you about uncertainty in hydrological and water resource modelling.
Okay, thank you very much. And it's really is a joy to be here and learning so much from you and exchanging ideas in this very wide-ranging colloquium. Let me begin this morning with a rather humbling tale. What you're looking at is the aftermath of the widespread flooding in northern Victoria, Australia, in January 2011. And the little town of Kerrang, with a population of about 4,000, saw their levee collapse on something like the 19th of January 2011. And the mayor of the town was obviously extremely concerned about the impacts of this event on his township. And in particular, he was concerned about how the flooding might impact critical infrastructure, in particular this power substation. And he recognized that no help was coming, either from the government or the power company. So he mobilized the whole town to essentially dig up roads, dig up the surface of the landfill, and construct this temporary levee around the power plant. It's about 800 meters, probably, the full perimeter. It's a huge construction, just built by the locals. And they kept their power station dry, they kept the lights on, and although many homes were flooded, they at least had a power supply. And I found that experience humbling on two levels. One, I met families who were still sleeping rough on the floor 6 months after the event, who'd lost essentially the whole of their livelihoods and were having to think about selling up the family farm and moving out. And it sort of brought home to me that sometimes as modelers and researchers of climate change, we can overlook the huge human implications of our work. The second thing, it taught me that no amount of fancy modelling is ever going to be able to capture that kind of spontaneous adaptation. So we have to approach all of this hydrological and water resource modelling with a fair pinch of humility, recognising that even with the best models in the world, we're still not going to be able to account for all aspects of human agency and decision making. Perhaps I should ask Rob whether or not you have that sort of spontaneous tearing up the roads and building a levee type option within your set. Maybe not. No, but okay. Well, yeah, rhetorical question. Okay, but you take the point. Yeah. Okay, so what I'm going to try and do is situate this whole huge topic of hydrological modelling and uncertainty in a much wider framework, and then systematically step through some of the key components of uncertainty relating to observations, model structure, parameters, and so forth. And then illustrate how we've been doing this sort of an uncertainty analysis for a couple of decades now, and then move on to a few short case studies which illustrate perhaps a smarter approach to combining and analysing and exploring uncertainty before wrapping up with some concluding remarks. So first up then, the bigger picture. Why are we doing this stuff? And I think back to Rob again, these two schools of thought really, in terms of impacts modelling generally and hydrological impacts modelling specifically. Two paradigms, the so-called top-down scenario-led approach we've heard a lot about so far, where the task is to essentially predict the future, characterise the uncertainty, and then act. Much as we might do with a sort of a forecasting type of approach. The alternative is to say, actually it's so uncertain that the best we can really do is to think more from a bottom-up approach that we saw yesterday, where we first of all begin with the option set and then think about how those options or policies perform in the context of climate and other uncertainties. And those two schools of thoughts or paradigms, it's important to recognise them because they shape the way in which we approach the whole modelling exercise and how we utilise the hydrological model. So I just want to set that broad framework out to start with. In the predict then act type approach, we might spend a lot of our time quantifying every aspect of uncertainty we can to characterise the range of uncertainty and the contribution of the various components to the overall uncertainty. With the assess policy or the decision-centric approach, we tend to use models as virtual laboratories. So they're sort of representations of the real world, and it's a mathematical laboratory within which we can explore options and decisions. And that's a very different approach, and that's what I'm going to be focusing on with the two case studies. And then finally, we can look at the hydrological modelling at two different scales. So traditionally, we have perhaps taken climate model information, downscaled it to the resolution of an individual river basin, and undertaken these so-called offline experiments. So the hydrological and the climate models are not coupled. They're related through a cascade, through the downscaling and so forth, but they're not coupled. Now, increasingly with Earth systems modelling, we're seeing much more sophisticated hydrological representation in global models. And in some respects, those global models are very much like those that we're running at the catchment scale. They're hard to tell apart. So we now have this capability of analysing global level changes in drought, flood risk, extremes, as we saw from Claudia's talk earlier in the week. So in a typical offline hydrological modelling study, like this one by Dobler et al., we look at the different GCMs, in this case 3, we might look at different regional climate models, different downscaling approaches, different hydrological modelling configurations. And basically we try to accommodate as many permutations as we can to explore the uncertainty. But the point is that this is entirely decoupled from the global climate model. Here is how these Earth system models are increasingly seeing the hydrological cycle. And as I mentioned before, it's converging on the way in which catchment scale models actually envisage hydrology. They're very, very close now indeed. So from your year 1 lectures, no doubt, you can remember the basics of the hydrological cycle: precipitation in, evapotranspiration out, runoff out. That's essentially it. And you've got all of the other mechanisms in between. And when we look at a figure like this, either on the left or the right, recognizing that there's a spatial dimension to this too, you think, well, how hard can hydrology be? I mean, this looks quite, look, this looks pretty tractable, doesn't it? Okay, you know, it's not, how hard can this be? But again, let's just be a bit humble about this. This is, if you're if you're concerned about future hydropower or water resources in Central Asia, this is the sort of environment you're working in. So you've got receding glaciers at high elevations, often semi-arid environments, so rainfall when it comes is patchy in space and time, highly complex terrain. And in this case, I look at this and I think this is one of the areas I've been working on recently, where one of the river basins is about 100,000 square kilometers, so 10 times the area of the River Thames, and we've got one meteorological station in that whole area. So I look at a picture like this and I think, well, if I had one rain gauge or one thermometer, where would I put it within this landscape to maximize the information content? So even the temperature, which we regard to be spatially conservative, is obviously varying massively with elevation. So if you choose to situate your thermometer too low in that catchment, and then you're using it to estimate lapse rates and hence snow accumulation and melt at high altitudes, you can be seriously out of kilter in terms of calculating the water balance. So let's be honest right up front, even before we worry about the modelling and the climate scenarios, patchy observations is clearly a key source of uncertainty. And even where we have the observations, obviously at the scale of an individual meteorological station, there's a lot that can go wrong. I ran a Met station for 2 years, and believe me, I learned everything that's possible to go wrong when it comes to measuring rainfall and just reading off the temperature accurately. There's so many ways in which errors can creep in at the instrument level. And of course, every observer has different tendencies, biases, and so forth. And the lady on the right-hand side was in charge of this meteorological station for, I'm reliably informed, about 40 years. So at least in this case, we have a single observer. So we can discount change in observer as a source of uncertainty. You can see that just from the nature of the equipment, it's looking a bit tired, and one has to question how, the reliability, for example, of the temperature measurements in that Stevenson screen as it's aged. And then once the paper records are submitted to the office, this is where they can sit again for decades before someone like me comes along and says, have you got any rainfall or temperature data for this catchment? And then begins the next step of digitizing the data, quality assuring individual readings as best we can from scant meta information, and essentially rescuing this resource for future generations. And again, we shouldn't underestimate the importance of that bread and butter work to just simply digitize and share data more widely. So let's imagine we've got our data now and we feed it into our simple snowmelt runoff model in this case. We might also rely on satellite imagery to tell us the spatial extent of the snow cover with this particular model. So here's what I call a nasty simulation, where those of you with excellent eyesight will see the grey line here. That's the actual observed river flow, and the black line is the model best estimate. So I don't think we'd pass too many tests based on that one, but that's the best we could do with the calibrated model, and the other lines then relate to the climate scenarios. So of course all of that uncertainty from the imperfect hydrological modeling is being fed into the subsequent impact assessment. Let's imagine we have twice as many snow cover images in another year. You can see straight away the difference in the quality of the simulation, because here we've got more information about the snow cover and its rate of melt with which to constrain the behavior of this model. And although it's using identical parameters to run, you can see straight away a radically better simulation in this case. So just having twice as many observations can help. Then we even have to question the quality of the thing we're trying to model. So let's imagine we're trying to simulate just annual runoff. And in this part of the world, there's some of the world's largest earth-filled dams. And for example, Toctogol, behind here, sits something like 20 cubic kilometers of water. Hard to imagine the scale of these structures. So when it was built in the early 70s, whoops, somewhere down the bottom there, you can see the sag in the flow as that huge space was filled. So if we were trying to model the actual observed flow in total ignorance of what was going on upstream, we'd be wondering why we were consistently overestimating the flow. And it's simply that we've taken 20 cubic kilometers of water out of the system over a 4 or 5 year period. And we might as well know of the existence of other structures such as irrigation and diversion channels. We know that they're there, but we have little or no idea about the amount of water that's being siphoned off to grow cotton in Central Asia. So again, how can we factor that into the modelling, which is then subsequently going to be used for the climate impact assessment? And even at the scale of the individual river, where we typically relate the amount of estimated flow to the depth of flow using these so-called rating relationships, we might have observations, for example, up to, in this case, this is a small headwater stream of about 80 centimeters of depth of flow. And then we have one extreme event on, say, the 5th of July. That's the depth of flow measured in the system, and you can see how much extrapolation is involved from that rating curve to get that value. So can we trust those high-end values? They're the ones that we might be particularly interested in terms of the societal consequences. But whenever I see a flow gauge with more runoff upstream than downstream in a 20-kilometer section, alarm bells begin to go off. How can this be when I know there's no diversions, no structures in between? Something's not right there. So it can be as simple as extrapolating a high-end event from a rating curve, and those uncertainties, again, are not explicit in much of our modelling. They're hidden in the data, and yet they are propagated into our impact assessments. Okay then, so let's move on to the different types of models, and I'm just going to really sketch out 3 types. So the simplest possible model that we might develop would be just a water balance, a simple accounting exercise where we essentially say the river flow equals the amount of rainfall in minus the amount of evaporation out, and then we might adjust that for melt from glaciers, in this case related to the rate of warming. We might adjust that for changes in storage and diversions. And that looks pretty simple, pretty appealing. How hard can that be? But again, we're applying an equation like this over, let's say, 100,000 square kilometers. How do we even estimate P, for starters? Do we have reliable information on the glacier response to temperature? How do we estimate evaporation in this environment over such a huge area? And as I've already mentioned, we have no idea about the extent of the divergence. So there we're just simply estimating the values from the cross-sectional area of the structures and saying this is perhaps an upper bound amount of flow that you could get through the structure. You're making those sorts of crude approximation. And the red and the blue lines show the extent to which the simple water balance performs in 2 large river systems. And you can see that the red matches the blue. The observations are the red. They match up to the end of the training period because they're constrained to up to 1990. But then beyond that, there's a divergence between these 2 lines. And we can only speculate as to why the modelled flow is greater than the observations? Is it that regional warming has enhanced the evaporative losses? Have diversions increased? We have no idea as to why these two lines depart. The second, and perhaps one of the most popular approaches, is the so-called conceptual rainfall runoff models, where we think of the hydrological system as a series of boxes, stores, and flows, pathways between these storages. And so we might have an upper soil horizon, a lower soil horizon, and these govern the amount of water moving down into the unsaturated and then the saturated groundwater zone, and eventually into the channel. And in the more elaborate models of this kind, we might develop each of a conceptual model like this for each of the zones shown in the right-hand side. So you might have a separate submodel for a chalk zone, for an urban area, or a rapidly responding clay zone. And models of this kind typically have at least half a dozen parameters, so things that we have to tune in order to fit the model between the rainfall and the runoff. Now, if we've got 3 zones, that makes it up to 18 parameters. But some of the earlier models could have had 25, 30 parameters that have to be tuned. So straight away, you should be thinking, that gives you a lot of flexibility, a lot of ability to essentially curve fit. You've got so many degrees of freedom, there's a real danger here of overfitting the model to your observations, and I'm going to come back to that later on. Then, of course, more sophisticated is the so-called distributed physically based models, where we're trying to apply physical laws at a grid-by-grid level. And here's Xitran. If you want to know more about Xitran, go and talk to Liz. But you can see straight away on the right-hand side how data hungry these models are. Now, things are moving on because we have remotely sensed data sets. We have a lot of gridded data. So as I understand it, Liz is now able to apply a model like this to the whole of the UK because we have the sufficient data to do this. But that's a key limitation is that the shopping list of information needed to run this is non-trivial. And so you're not going to be able to do this everywhere. And then we move on finally to the water resource management tools. So this is where we actually take the simulated hydrology and then pass it through an additional set of algorithms to represent decisions made by water managers in terms of the operation of reservoirs, the transfers of water between cities or sources and demand points, groundwater abstraction, the return of water from water treatment works, and so forth. And this looks nice and simple on the screen, but believe me, this is a really painstaking task because you have to literally quantify the rules governing every little point and exchange in this whole system. And that can involve hours, days, years even, digging around in the water legislation to figure out who can take what water when and how much. So this is a truly non-trivial exercise to get to this point. And finally, I just wanted to mention that there is this other family of models which are beginning to emerge. And this is actually a pretty exciting opportunity where we have sort of generic modeling structures like FUSE, where we might have 4 different hydrological models which represent different treatments of soil moisture and exchange processes, infiltration and surface runoff. And with those sort of 3 or 4 sets of parameters, we can take them in different combinations, and with this single structure, we can emulate 4 different types of hydrological model. And just in this case, there's over 100 possible model combinations that one can construct within a single modeling framework. And the figure on the top right-hand shows the extent to which this generic structure shown in the grey line is able to perform better on average than individual models that are being compared against it. So the Nash-Sutcliffe score is a measure widely used by hydrologists to test the skill of a model, and a rule of thumb is anything over about 0.6 is considered as a reasonable representation of the hydrology. So you can see that this generic model is performing pretty well when compared with individual models. But that presents perhaps one self-contained system in which we could really dig in and explore structure and parameter uncertainty in one framework, should we choose to. I just wanted to mention one variable that is often neglected, but is attracting greater attention now, is the effect of climate on evaporation. It's kind of the neglected variable. We tend to focus on rainfall runoff and say, well, yeah, we can just apply Thornthwaite or one of these other methods and estimate evaporation, no problem. But when we actually compare different equations for evaporation as shown in the top left-hand corner, we can get radically different answers from the same data, the same inputs. And these are more or less sensitive to temperature. So as we go forward into the future, those differences between the different evaporation algorithms begin to stretch out, and that can really have a big effect in terms of the computed runoff. And here, for example, back to that site in Central Asia, we looked at how the change in annual potential evaporation responds to the choice of equation, to the choice of GCM, and the choice of emissions. So by the 2020s, we've got a range of about 0 to 10%. So that's within measurement error, really. The 2050s, we're getting up to 0 to 30%. And by the 2080s, because of the temperature forcing, a range spanning nearly 70%. So you can see that this is potentially a very significant factor in our water balance estimation, and we should not really be neglecting it or assuming it to be a stable quantity. Okay, so let's look at parameter uncertainty, and going back to this catch-mod system where we have about 6 or 7 parameters, and I'm just going to illustrate just for 2 of these parameters the extent to which we can get very different results from just messing around with these 2 parameters. So the PDC is essentially a parameter that determines the rate of evaporation from the upper soil horizon. So for values smaller than the PDC, evaporation occurs at the potential rate. Beyond that, it's diminished, it's constrained by soil moisture. Direct percolation is a very, how can I put it, vague variable. It's a way in which the hydrologist can take water from the rain and essentially avoid the soil horizon and put it straight into the unsaturated zone. And it's really a cheat to enable the groundwater to respond more rapidly than we can think of in any other way. So if we take that direct percolation variable, we can vary it across a value of 0 to 100, and we can vary all of those other parameters, the other 5 or 6, simultaneously using just simple Monte Carlo sampling methods. So each dot represents one simulation of this hydrological model with a randomly chosen set of parameters, but where we're essentially ranking the DP. And you can see that within that cloud of uncertainty, there is an optimum value somewhere in the region of 50 to 60%, where you're getting that Nash score of 0.6. But if we stratified the data by wet years and dry years, we can see very different behavior. So it's straight away telling us that the choice of parameter is really dependent on the information content of the training data set. If we happen to calibrate on a dry period or a wet period or somewhere in between, we're going to arrive at very different optimum parameters. In a nasty case, such as the potential drying constant, we can do the same exercise and pretty much you can choose whatever value you want. There's hardly anywhere in this cloud a point at which you could say this is the optimum parameter value. It's a very poorly constrained, a very poorly defined parameter within this particular hydrological model. But this touches on this critical issue within hydrological modeling of equifinality. This notion that different combinations of parameters can yield identical model performance. And the same concept applies to GCMs. I think Chris mentioned earlier in the week how there's trade-offs between, was it the climate sensitivity and the aerosol forcing? So you can have permutations of just those two parameters that produce very similar results for the control run. Obviously different results in the future. That's exactly the same principle with the hydrological modeling. So then when we take those uncertain parameters and then apply them, again, in this case to the River Thames, and I've just pulled out results for one emission scenario, you can see it kind of makes about a 5% difference in the wash up to the 2020s, about 10% by the 2050s, and a little bit more by the 2080s. So it's not a huge source of uncertainty, but it is uncertain. And for me, the key concern is the fact that the parameter choice is determined by the information content, the nature of the climate regime during the training set. And that determines, to a certain extent, how that model is going to behave in the future climate that you impose on the model. To me, that's the larger concern about this equifinality issue. All of these models are equally plausible, and just for comparison, the EA, the little cross, is the value that the Environment Agency determined by just manually calibrating this system. So the hydrologists did an amazing job in a way that without running 10,000 Monte Carlo runs, they were able to apply professional judgment and set the parameters in a way that far more exhaustive analysis took a weekend to complete. Okay, so we've explored some of the components of uncertainty, going from the inputs, the actual model structure and its parameters, and the outputs. How are we going to use this now in NCAR? And Haley introduced this framework, an earlier version, which was completely filled in. In this later version, I'm acknowledging the fact that we simply don't have the computing resources, the time, and probably the inclination to model everything within this triangle. So in reality, we're only sampling some of the emission scenarios or RCPs. We're applying some of the regional climate models, some impact models. We're thinking about some of the local consequences and some of the adaptation responses. We just can't fill this whole thing in. So that means that inevitably we are only exploring some, but not all of the range of uncertainty. Even if we could throw everything, every model, every resource at it, the likelihood of thoroughly capturing the full range of uncertainty is probably close to nil. And Ed Hawkins produced this, well, I think this is a wonderful diagram, where he actually said, well, does that uncertainty cascade really exist if I take actual climate model and plot it in the same way? And that's what he did with the RCPs for different time horizons and different climate models from CMIP 5. And this is, again, for the same region in Central Asia, we can see how the cascade of uncertainty stretches, how individual outlier model emissions scenarios and time period combinations can take us right out to the left or the right. And as a reasonable rule of thumb, I tend to refer to the plus or minus 42%. That's if you assume plus or minus 42 for the range of uncertainty in rainfall, you're never that far out. Pretty much anywhere you go. Okay. Yeah, sure.
Is that raw climate output or
Yes,
bias corrected?
This is raw information, as far as I'm aware, and it's being averaged over quite a large area, so there's no downscaling in here. So we could have gone the next step and say, okay, let's take this information and downscale it, and no doubt the range would extend still further. Okay. Now, if we did that, we take the different climate models, emissions, the downscaling, the hydrological impact uncertainty, we put them all into the wash, again for this region in Tajikistan, and then finally we put it into one impacts model, in this case a hydropower energy production model. You can see the range of uncertainty that we get. So this is, in my view, sort of the logical consequence of this top-down approach is we are going to arrive at a very large range of uncertainty. We might be able to characterize the source of that uncertainty, but what are we actually taking to the decision maker or the investor who's got, let's say, $60 million? He or she's thinking about investing in a new hydropower plant or upgrading a plant. What are we going to tell them or advise them about the future climate in this framework? And a couple of years ago, I was fortunate enough to be asked by the World Bank to look at how they, as an organization, had been using climate models across their entire investment portfolio in terms of the water sector. And we produced this simple typology. And the striking thing that emerged from that analysis was the overwhelming reliance on this scenario-led approach. And having gone through that exhaustive analysis of all the components that was feasible, how often the authors or those undertaking the study would arrive at rather loose, these sort of low regret solutions, which is reduce water demand, manage the soil and the land better. Those sorts of very general best practice remarks invariably emerge from this approach, because there's not much else you can really do. You certainly can't make a specific predict then act type recommendation. Okay. Oh, sorry. Yeah, I should say that they're the number of studies where the trait was exhibited. So the sample size was small. It was about 30 studies, but these reports can be pretty huge. So 30 large reports. So that is where the conventional top-down framework, where you begin by exhaustively modeling every emission scenario you can, every downscaling approach you can, every impact model you can, arriving at a result like that, and then saying in the final chapter, what are we going to advise? And it's often save water, manage the soil better, or something like that, as a low regret measure. So I prefer to use the term low regret to no regret, because there's always an opportunity cost associated with even managing the soil better, even though it makes sense.
People focused on a single scenario, and did that change the policy outcome?
I'm trying to think. I think most studies recognize that the GCMs are a significant source of uncertainty.
Yeah.
So to nail your colours to the mast of a single model would be
Probably, yeah.
probably
Create an
unwise.
alternate universe,
Yeah.
but I wonder if in fact you would actually get people to focus on a different outcome, so they might still end up with the same endpoint.
That's a good question, and one I could go back and look at, because that would be quite an interesting insight in terms of what they actually did with that one model. Okay, pressing on then, I just want to touch these two case studies. What's the alternative to this top-down scenario-led approach? And first example I'm going to use is some work by Sean, sitting right at the back there, who worked on this analysis trying to explore hydrological change in the River Boyne. But the important point, the reason I've chosen this as a case study is because we're using the hydrological model with all of hydrological models, plural, and parameter sets, plural, with all of that uncertainty that I've mentioned before, as this virtual laboratory within which to explore multiple hypotheses of observed change in that system. So what's going on? It's a different approach. So the study was prompted by this notable step change. So this is the river flow in the Boyne, and it was observed in the late 70s that this step change. So at the time, those writing about this dramatic change only had data up to the late 1990s, and this change in the environment was attributed to a shift from a strongly negative to strongly positive phase in the North Atlantic Oscillation, which is essentially characterized by warmer, wetter winters. So that's entirely plausible. You have 30 years of warm, wet winters. Not unreasonable to expect the river flow to jump so dramatically like that. But there are a lot of alternatives, actually, to explain what's going on. So within the group, we tried to come up with a shopping list of plausible explanations for that step change. And some, shown in the red, could be dismissed relatively early on. So Sean and his supervisor, I think, went to the hydrological service and established that it wasn't due to poor quality data, looked at the meta information, it wasn't due to abstractions or diversions, and a close inspection of the evaporation data told us that that had remained pretty much constant. Then we've got other possibilities such as changes in treated water, urbanization, expansion, which has happened to a certain extent, changes in woodland cover, and combinations of other drivers. But perhaps the most plausible explanation is this expansion of the drainage system, which was financed by the government, or was it the EU, essentially to encourage more production, wasn't it? Okay. So dramatic change to the surface hydrology of this basin. So what was done was the model was calibrated on this pre-drainage period, which you can see on the far left-hand side, using 3 hydrological models and over 300 what we call behavioral parameter sets. So these are parameters that perform equally well. They're the equifinal values, combinations that give a good performance for this system. And you can see that those 3 models shown in the different colors fit the hydrology pretty nicely, and then and were tested outside of the drainage expansion period. But then running forwards, you can see that that model does not reproduce what we observe in that system at all. We can see it's consistently underestimating the observed flows. And you can see that on the bottom right-hand side, where we've got the cumulative flow, gradual deviation from that observation going forward. And this can be broken down by month. You can see that that long-term bias just isn't there in the summer data. The hydrological models and parameter sets span the observations quite nicely, as you'd expect. Some pluses or minus, it's on either side. But then going through the winter months, shown in the red box, there's a big deviation between the observed and the simulated. So that's saying to us that whatever it is that's driving the hydrological change is happening in the winter months. That's when this model is unable or least able to capture the observations. And what we can then do is run the model and inspect the data for change points, and we can then reconstruct essentially the hydrology of this system as it would be had there been no expansion of the drainage. Am I still okay, Sean? Yeah, good. Just checking. So you can see, yes, there has been a jump at that tipping point. So we might speculate that the North Atlantic Oscillation, the changes in the rainfall properties in the winter, has contributed to some uplift, but not the full uplift shown in the red line. So this simple example shows the way in which we can think in a little bit more detail, try and explore the sensitivity of the system at a more process level. So we're not essentially using the hydrological model as a black box, and it's helping us to understand, well, how might this system respond in the future, and what is the relative significance of a land surface change compared with climate variability. You can see that the difference between the two. Okay, moving on to case study 2, conscious of time here. This is some work that I've been doing with Dave Yates and Kathy Miller to explore one adaptation option for the upper Colorado River Basin. And to do this, we've been working closely with Denver Water. So I was looking at Rob's presentation yesterday and thinking, wow, you've covered it all. Where does this sit? We just looked at one option, but we did look at one option in a great deal of detail, and I think there's still some useful insight from what we've done. Although I must admit, I was a little crestfallen after yesterday. Okay, so if we turn to the bias-corrected downscaled information for CMIP3 and CMIP5 for the whole of the upper Colorado River Basin, we can see that temperatures expected by the 2050s will change by +1 to +4 degrees Celsius. That's across the full ensemble range at this scale. And rainfall is expected to change between -10 and +20%. Again, averaged over the whole basin. So we can begin the analysis by accepting that uncertainty is a fact of life. So we essentially don't know what the future regional climate will be in this basin. We've got a best estimate in terms of the range. So the question is, how might adaptation options perform given this range? So I think it does kind of, in a way, mimic the approach adopted yesterday, which is to explore portfolios of options within a plausible range of conditions. But it's a very complicated system. Climate variability and change affects not only precipitation and evaporation and so forth, it has indirect consequences for a whole host of other factors that could potentially affect the hydrology of the upper Colorado River Basin. So what are the indirect consequences for wildfire, flash flooding, dust on snow events, which are increasingly recognized as a concern, where dust is carried from the west, drops on the snowpack, and accelerates the rate of melting and changes the timing of the melting. So that's again, a very subtle process, but one that if you don't include in your hydrological modelling, you could be missing quite an important feedback from regional climate change. And then we've got the hydrological system itself, which is comprising lots of reservoirs and transfers of water over the mountain range to Denver. Public water demand, which is also sensitive to climate in terms of temperature, the length of dry spells, cloud cover, and so forth. And there are a range of other users. So water's having to be set aside in the Colorado to keep the rafters happy, to keep the bugs and the fish happy, and to keep the irrigators happy. So there's a huge amount of competition for this water, and we're trying to keep everyone happy under this broader context of uncertain climate change. And this is a simple representation of the water supply system, as I mentioned, made up of reservoirs and tunnels and so forth. And the way that the water system works in this part of the world, crudely put, is first come, first served. So if you're there first, you get senior water rights, as in the case of the Shoshone, I hope that's pronounced correctly, power plant, which acquired the water rights from 1902 and 1929, so it has the first call on the water. And then later along, we have the Moffat Tunnel, Green Mountain Reservoir, Wolford, Williams Park, and Dillon reservoirs. So these essentially are ordered in terms of their year of seniority, in terms of the order with which they can take water from this system. And the basic idea in terms of the adaptation is that what would happen if the power plant gave up temporarily some of the water rights to enable earlier fill or more fill of the reservoirs upstream to try and capture more of that spring runoff? Would that enable greater resilience to droughts? And that mechanism is triggered when reservoir levels are at a particularly low level, when I think it's related to watering in Denver. There's controls on lawn watering and so forth. So that's essentially the system. So we turn to WEEP, and Dave Yates took, I think it's fair to say, best part of a year to try and capture this system, all right, within WEEP. Again, how hard can that be? Well, look at that. This is a replication of some of the protocols used by Denver. And I'm not going to drill into the detail, but you can see how when you drill into the paperwork of who can take what when, and you try and structure it into a flow chart, it becomes incredibly complex. And I'm really glad that that was Dave's job and not mine. All I had to do was build a weather generator to simulate daily temperature and rainfall across the upper Colorado River Basin using my downscaling tool. So here's a validation test, I believe, of the model's ability to simulate rainfall and temperature distributions to reconstruct interannual variability, and then the dots show the intersite correlation. So I was reasonably happy with those outcomes. We then explored not only the sensitivity to the climate forcing, but we also applied what we call these narrative scenarios. So we wanted to take a far more holistic view of the system. So not just forcing the temperature and the rainfall through this, we wanted to think about how the climate change might indirectly affect vegetation cover or trigger dust on snow. So we represented these additional factors by tweaking some of the hydrological parameters to affect the snow melt, the runoff from previously vegetated areas. And we can imagine these scenarios vegetation change as a consequence of fire or beetle attack, which might be driven by the drought, the very same drought scenario that we're using in the downscaling. So we're just trying to take a far more holistic approach to this system than one might normally do. Without going into too much detail, the coloured lines essentially show for the top three scenarios, the narratives that I've described, essentially earlier spring melt, so nothing surprising there, but varying degrees of earlier spring melt and changes in the magnitude of the runoff. And you can see as well on the right the interannual variability. It's actually the red line, the vegetation change, whether by fire or beetle attack, which seem to have the most profound impact on this system. And if we looked at an individual year, we can see a lot more detail. We can see this subtle shift in the timing of the runoff coming a few weeks earlier, and we then ask ourselves, well, how does that interact with this adaptation measure that enables more water to be taken? And in some ways, rather disappointingly, the result was nil. So it's one of those studies where you kind of expected the adaptation measure to have an impact, but when you actually think about it, it enables greater water take during the time of the year when the climate change is favouring more runoff. And during that period, the water company, as I understand it, already has seniority of rights, so it hasn't actually enhanced the ability to take any more water than could be taken anyway. So what we essentially learned from going through this process was that we were happy with the narrative approach, that we think we're exploring the behavior of this system in a more holistic and plausible way, and we're bringing to bear the best available scenarios to test the sensitivity. We looked at the extent to which greater flexibility in the water rights can or can't help adapt to the change. And perhaps most importantly, we were all the way through exchanging information with the water company, trying to gain an insight into the operation of that whole system. And that, because it can sometimes hang on these tiny deep points of detail and subtlety in terms of the water rights and so forth. So this is a very labor-intensive exercise, but we gain a lot of insight by doing the work beyond yes or no, the adaptation measure helps. So I console myself that it was still worth the exercise, and I hope Dave Yates feels the same way too, having done all that wheat modelling. Okay, so just to wrap up then, three final thoughts. I hope this talk has shown you the extent to which essentially uncertainty can just blow up. It can expand over huge ranges if we take this conventional top-down approach, try to characterize every element in that cascade. And I think that is an entirely legitimate scientific exercise, a legitimate area for inquiry to understand, for example, the sensitivity of findings to things that are often hidden, such as changes in evaporation. So it can reveal elements of this system that maybe as a community we've neglected a bit. So I think there's lots that can still be legitimately done in this so-called top-down approach. However, I think where we could be doing more is in the latter group, where we're using the models of the system, we're using these broader narratives to explore options, to explore key governing processes, dust on snow, beetle attack, fire, or fire with flash flood and dust on snow, sort of the nightmare combination. We can drill in and understand the processes affecting timing and volume of flows in these systems. And I guess the final remark is that there is still a huge amount of research to be done, particularly in the data-sparse regions that I showed at outset, where we need to be developing more techniques for data infilling and estimation to assist impacts and process-based studies. And also maybe using our regional climate models for those regions to explore the key governing processes and feedbacks from those land surface changes and the atmosphere. And I think that link between the hydrology, the land surface feedbacks, and the regional downscaling is again a fruitful area for future research, and hopefully we'll be hearing more about that later today. Thank you very much.
Thanks very much, Rob. Great timing. Really good timing. There must be lots and lots of questions out there.
Oh yeah, here we go.
Where are we at in terms of integrating state-of-the-art hydrological model in GCMs in terms of like two-way interaction with the climate?
I'm probably not the best person to answer that. I mean, I showed you the figure to start with as an example, the hydrology in the community Earth system model. I think my understanding, Chris may correct me, that these models, and it's not just within the GCMs, it's a sort of perhaps a limitation of all of the so-called grid-to-grid models, is their ability to represent things, the groundwater. I think the groundwater system, which it can be obviously very important for...
So we need a very fine resolution, like finer than a kilometer?
Well, it depends, again, in terms of what the ultimate application of the model is for. If you're interested in, let's say, the global pattern of drought, both in terms of its spatial extent, severity, and duration, then large scale is probably adequate. But if you're concerned about how the ecology of a particular river system might respond in a perturbed climate, if it's groundwater dominated, it's feeding cool water and sustaining flows in summer months, then you need to have a really good model of the groundwater system, and for that you need much finer resolution.
And high computational resources, probably.
Depends on the application. Yeah, you probably would you seek to apply that sort of level of analysis globally? I mean, people have obviously tried to model freshwater ecosystem impacts globally, and you can do that in a crude way using indices, but you're missing the really important process level information in terms of how the bugs, the fish, and the flows, and the water quality, and the temperature of the water all interact to affect the outcome. So it depends on the application.
On the groundwater issue, that's the cutting edge at the moment in terms of climate modeling and going to high resolution. So the DOE in particular is heavily involved with this water resource management question and how that's going to be developing in the next few years. So, okay.
Thank you.
This is a little different. It's more local. I'm interested in how these models could be used for attribution of, so there's a case in Minnesota where they have a lake where the water levels dropped like 25 feet, and multi-million-dollar houses have lost their value. So they sued the state for mismanagement. But then some people are claiming that it's actually climate change that's causing, the change in water levels. And they did a statistical analysis, but I'm wondering how this kind of modeling work might be useful, or how it might stand up in court, or just thoughts on that.
Well, I think I would. What the situation you've described to me sounds very similar to the situation in the River Boyne, where you have an observed step change in the system, a shopping list of a dozen or so potential causes, both in isolation and importantly in combination. That's, I think, one of the key findings from this study, I think, was we couldn't necessarily pin the step change on a single driver, i.e. drainage change. We speculate that it was drainage change plus rainfall change and maybe some local urban influence that we were unable to quantify. So I think you could use this hydrological modeling system and this approach of multiple working hypotheses to explore the plausibility of these different changes in catchment and boundary conditions. But I can't think of any particular example where the next step of taking that into a courtroom and using it in either defense or against someone for damages. I can't recall any example of that.
Do you think that's something that's possible? I just know that this is a big issue. I mean, I just looked it up. It looks like they have a $600 million agreement now. You know, and that's it. I don't know what's going to happen, but I know that I talked to the judge and she's like, I'm not sure what to do.
Well, I mean,
you know, and I'm not I'm not an expert, and also they didn't have, you know, it's uncertainty, and this is where I think it's really interesting, and they're like clamoring for information, you know.
So what you're asking me for is some freebie advice here. I should be charging you by the minute.
Well, yeah, I mean, not for me, for them, who they aren't even here.
Yeah.
So.
What's the rate for that then, Joel?
I'm just interested if it's something like you're confident that enough to say like
I think there's, you know, you can go down that line where you take it to court clearly and have all of those legal and technical arguments, and one group can find one technical expert who can say this, and another group can find another technical expert that says the opposite. But probably the preferable route would be within some forum of all of the parties sitting down together and saying, you know, how can we work this out so we optimize the benefits to as many people as possible, we manage the risks, we maximize the benefits. How can we manage this system better as a collective? That might be, you know, whether or not there's any opportunity to explore those avenues, I don't know.
But then the modeling. Sorry. Okay. Sorry. I'll ask
later. We've been playing around with that question a little bit for US EPA or related questions, and so I mean 2 points. One is, I think you raise a really interesting issue. I think I think you need I think you can't just insert new information into the existing process, and so the sort of the rules, expectations, and stuff like that need to be twiddled at least a little bit to put in a new set of information. And so the stuff we're doing is sort of gingerly getting towards that. And people obviously are really sensitive to how you change the processes and such like that. But I think in some sense the particularly, and you're talking about the really extreme end, which is once you've got an adversarial legal process going on, which it's pretty hard to start changing the rules of evidence and stuff like that. But so I mean, I'm kind of generalizing or making specific your point that if you think you're going to have more of these sorts of situations in the future, you might want to start setting up the underlying legal institutional structure so you can deal with information. Well, that information that may change over time, and then how do you set up a process that works? So you might think in some instances that there'd be like a common pot that people put in if they're doing certain sorts of development and things like that, and that you use it to allocate to people who as the data changes, some people are going to win, some are going to lose, and use it sort of risk sharing sorts of things. But you have to start thinking mechanisms along those lines.
I just really had a quick comment. There's a really good book called The Civil Action. I don't know if you read it. It's about groundwater pollution in a small town in Massachusetts, and about the whole legal process that went through it. And both lawyers actually hired, expert hydrologists to support the case. So, yeah, you have the experts on both sides telling you different things.
Finally. Oh, go
So I know there's a lot of questions on that, but can I change the question?
I'd be happy if you did, actually.
Okay. So my question is more about the issue of overfitting with these models. And there might be a couple parts, but the first one is, do you find that it's harder or less likely to overfit with process-based models, hydrologic models, than more empirical lump models? Or do you see it being the same exact issue across those models?
I think it's probably dangerous to generalize. I think that my personal preference is always to work with the most parsimonious model I can, but there's a trade-off between having a parsimonious model and having adequate process representation. So the conceptual model that I showed you was developed in the 1980s as a water resource management tool, and there are some of those parameters and processes you would be hard pressed to actually observe and measure anything in the field. So hence they are conceptual models. But at the end of the day, you're only having to calibrate 5 or 6 parameters, and what you find when you test the model performance using data outside of the training set, if it's stable and it gives a good performance, then you've got some confidence. But as I showed you, that the choices that you make in terms of those equifinal parameter sets, there may be thousands of combinations that give you the identical result during the training. The choices you make there matter depending on whether or not future climate fed in is warmer, wetter, or hotter and drier. That interacts with those parameters. So the golden rule, if you're going to take that approach, is to explore as much of the parameter space as you can, both in the training set and in the application side. So you're explicitly acknowledging the extent to which the parameter and the structural uncertainty can confound your scenario that you generate for the future. But it's the interaction between those parameter sets and the prescribed climate, whether it's hotter or drier, very wet, relatively cool. It's that interaction that matters. So again, you sort of try and interpret that in terms of the process understanding, the extent to which certain processes are being triggered more or less frequently under one climate regime than another. So it's always possible, and I think always beneficial, to try and interpret the behavior of the model from a process level, no matter what you're doing. Rather roundabout way of saying, I don't know.
So I was wondering if you could give a little bit more perspective on sort of the intended audience of this Denver water project, just sort of who the policy community was, if it's, purely for water managers or policymakers or whatever, and how the process, if how the process might have changed their perspective on what they could and couldn't do with climate information.
Well, one point that's come out, I think, through these discussions, not just in Colorado, but talking to others involved in the water industry in the US, is the extent to which that community has tried the conventional approach of putting all of these scenarios in and producing this big envelope of uncertainty, and has recognized that that can only take you so far. It's not really going to help you arrive at a decision or inform, give you insight in terms how options perform against each other. And so there is a sort of a willingness to explore these alternative approaches that I sense in the US, which is probably more advanced here than it is in the UK. I sense that perhaps, maybe Hayley will correct me, that the water industry in the UK is still very much sort of scenario-led in its thinking, and that's partly linked to the institutional structures and so forth, and the ways in which these analyses are prescribed and have been done historically. Although we do see lots of nice examples in the UK too of the bottom-up approach. But so when we began this collaboration with the water company, we were pushing on an open door. They wanted to explore this alternative approach. And so it was a meeting of like minds, and it was a way of saying, well, okay, what insight can we gain? And we were certainly gaining a lot of insight from that interaction in terms of the behavior and the governance, the minutiae of the operation of this water system. As a modeler, you need that collaboration. And, time will tell in terms of how the company would take forward this finding that this particular adaptation mechanism doesn't appear to offer a significant advantage. Does it mean that it has to be redesigned slightly so that window of relaxation where you can take the water is expanded or it's made more flexible? Perhaps that's the key insight that arises from it, that the basic principle is fine, but we may need to just adjust the detail of the operation of this relaxation agreement. That's a conversation that still has to happen, and then of course that's going to involve all sorts of other agencies, all of which have their own interests and concerns about protecting the environment, tourism, water for agriculture and so forth. So yeah, I see it as an ongoing process. It's definitely a dialogue. It's not scientists doing one amount of work and then presenting it as a de facto result.
I have a question over here. How useful to you were satellite observations like NASA's GRACE on evapotranspiration?
Sorry, could you start the question again? Yeah, it is.
I'm just wondering how useful to you satellite observations were on evaporation, like NASA's GRACE satellite, for your local case study, and if that was actually something that you could use in your model.
Yeah, that's not something we've investigated so far, although where is it? In the back of my pocket, I had some extra slides in case I got through in time. So I was going to talk about possibly this other case study in Yemen where we have done exactly that. We've relied on remotely sensed rainfall, vegetation, public domain topographic information, and the very sparse observational data, and blended all of those products into essentially a weather generator that enables us to then produce these really detailed maps. In fact, we produced an atlas for one of the UN agencies to direct investments in water infrastructure and so forth. So I'm totally sold to the idea of exploiting remotely sensed information, particularly in data sparse areas where we can meld it with surface observations and meld it with anecdotal information. So in the case of Yemen, there's virtually no information on river flow with which to judge whether or not your model of flash flooding is adequate. But what we have is newspaper accounts of loss of life and damages to villages. And those, for example, tell us that this part of the Yemeni highlands on this escarpment has a very high concentration of flash flooding, loss of life and damage. And this is exactly where this satellite surface-based modeling system predicts the highest incidence of extreme rainfall. So it's not an either or, it's not just all satellite, not just all surface observation, it's that plus using other proxy information, bringing it all together in one overarching framework. I think that's where we can really make some progress.
Just to clarify that the trim data set there is not the same as the GRACE data,
Yeah.
which is gravimetric data.
Yeah.
And that's active radar from space for those people who aren't familiar with it.
I'd a comment as well. We've done quite a bit of work on this as well in mountainous regions in the Himalaya. And I think it's really a useful thing to use remote sensing products, but it's a really it's a new field. And trying to work out how to use these products in the best way, whether you use them as inputs in the way that Rob's used them. We've used them also to constrain parameters within our model system, and also even things like using MODIS data to constrain lapse rates spatially and through the elevation range is actually quite a useful thing. But again, you've got biases within these products as well, which you need to account for. So you still really need observations as well with which to constrain the remote sensing products themselves. To add a comment on Rob's comment previously about the UK water industry, I think that all water industries really and water resources management systems are struggling with this scenario approach, and particularly in the UK, since we've moved to this probabilistic type approach, where you need to run multiple different scenarios through your models now. And much of that is to do with the fact that these models aren't really set up to run multiple scenarios through. They've previously used sort of worst case scenarios, like, for example, Northwest England, they've used the 1928 drought, for example, as being the worst one on record. And suddenly they have to run multiple runs. Yeah, I mean, I think you're exactly right that we still need this dialogue between water resource managers and the impacts community, really, and the scenarios community, to actually try and work out what are the best ways in which we can use this information, because really people are not using the information in the way they're supposed to be using it. They're really just picking one scenario or a few scenarios, whereas they should be looking at the whole range. Got time for a few more questions. Time for a few more questions, maybe two more.
Joel, did you want to?
Okay. My question is in response to your World Bank study that you made a reference to.
Yeah.
Funders are known to push certain approaches. For instance, in the 90s, there was this overwhelming push towards participatory irrigation approaches in India. And for instance, more recently, you see funders pushing for elements of user engagement and capacity building and things like that. So when resource-intensive computational resources are sort of used to arrive at solutions that are obvious and that are that pointed out towards no-regret options, what was the kind of... I'm just curious to know the response from the World Bank in that sense, as to on one hand we speak of uncertainty in our assessments, and on the other hand we point towards obvious sort of solutions. So I'm just curious to know what happened after the study.
Okay. It's clearly not right for me to speak on behalf of the World Bank, but
Go ahead.
I think what I sense is that we look at the academic literature, and I'm including in that successive IPCC reports, which are hardwired top down. We have working group 1 scenarios, working group 2 what happens next, working group 3 what we do at the end. So we, as a community, we're hardwired to think like that. We structure our undergraduate programs to begin with the scenarios and the climate science, and then towards the end of the module, the impacts and what we're going to do. Our literature is dominated by the same stuff. So it's hardly surprising that the consulting world is mirroring that approach. And I think part of it, when you've got a body of literature that's out there which is repeatedly implementing that framework, there's a sense in which there's a due diligence to comply with the scientific modus operandi. So there's a due diligence dimension, I think, to apply the state-of-the-art science. I think the other thing I've sensed is that there is a discussion going on, not just within the World Bank, but other donors in terms of, is this the most fruitful way? So I think I do sense that we're in a period of change where we recognize the useful insights that come from the approach I've just described, but we also start thinking about and exploring the possibilities and the insights that can be obtained through different approaches. And I've always found every World Bank project I've worked on, I've found the interaction incredibly thought-provoking, and as a scientist, as a hydrologist, working with teams of economists or agricultural scientists or whatever, it's you gain so much as a scientist working alongside these other groups. So I think we're as a community, whether in science or in consulting, we're in this period of change where there's a willingness to try different approaches and explore. So it's no criticism of anyone, it's just where we are.
Yeah, I disagree with you, Rob, about the IPCC. Although the structure is Working Group 1, Working Group 2, Working Group 3. In point of fact, we know that for each iteration of the various reports, the information generated in Working Group 1 is not actually used in Working Group 2 because of the fact that you can't have scientific simultaneity and temporal simultaneity. So it's always based on temporal simultaneity. In point of fact, Working Group 2, I'd say particularly this time around, if you look at that entire frame, and I showed that in my introduction, it's really the whole frame of risk assessment is really departs quite considerably from that focus. And so regardless of the fact that there's Working Group 1, 2, and 3, and regardless of whether Working Group 1 thinks they're the head honcho, in point of fact, the structure of the IPCC in terms of the actual assessment has really changed. And I don't think it's that linear top-down anymore, even though the three working groups are kind of, in a very superficial way, I think, set up that way.
Yeah. No, I mean, I accept that IPCC structures, reports, and so forth have clearly evolved with each iteration, and we've seen nice examples of the extent to which chapters on adaptation and decision support have permeated the latest iteration. But I just, as devil's advocate, I just wonder if there'll ever be a day when there'll be an IPCC Working Group 1 report on decision making or options, so it's human centric, decision centric from outset, and then we then proceed in terms of the structure of the report and the attendant evidence to think about how the science helps us. I mean, it's a tiny point of detail and not worth arguing about.
No, but I think it's important how this audience views the IPCC. The IPCC is not an entity where you're going to see major shifts in the structure of anything. And so I think, no, it isn't. I mean, it's just an incredibly bureaucratically and internationally politically maintained organization. So I'm just saying that I don't think you should use the superficial structure of the IPCC. It probably never will have that structure. I mean, ultimately, the IPCC should evolve into an assessment of sustainability. But that's never going to happen because that's not the way it was set up. So I just want to caution people to not overinterpret the structure of the IPCC as representative of what the true scientific community sees, how they see the problems.
Yeah, I'm not going to disagree with that. I just think that whether it's IPCC, historically, the way in which the science leads the decision, the way in which we organize textbooks and courses, that you know, I'm just being a little bit provocative. Maybe we could design an undergraduate course that has the climate science at the end rather than the beginning.
Isn't this it, Rob?
I don't know. Did we have the opening talk based on decision making? We did. Yeah. There we go then.
We're living it, Rob. I don't think you can really be a provocateur.
That's it.
In this context.
Okay, I think we'll take a final comment.
This is great. This is a fascinating session, and I think where we're ending up is exactly in the right place. That there has been this model, and I remember our friend Steve Schneider observed this. There was a model when we were first addressing vulnerability to climate change. How bad was it? And there is a scientific top-down model, and that 1, 2, 3 IPC structure makes a lot of sense. As we've dealt more with mitigation, but I think particular adaptation, I think Steve saw this too. Just taking that model and assuming it would work for adaptation was now in retrospect naive.
Yeah.
Nonetheless, it's still being followed. So I think what I was intrigued with in your Denver water paper, which I'd like to see, is this sort of co-production of knowledge, working with decision makers. In many respects, they need to be at the table thinking, what is it they need to know? What kinds of decisions? I also wonder too, it's why I asked the question, and I realize you can't do it. If you gave them a single scenario, they want a forecast. But if you gave them a forecast, what would they do with it? So it's an interesting question of even how they might use knowledge. But I try to emphasize now is working with them to understand what do you need to know about the decisions you're making?
Yeah.
What scientific input, how much confidence, and you make decisions all the time in light of uncertainty.
Yeah.
So how much, how would you factor this in, and then maybe you do the science to inform it rather than just running all the models and then blasting it at them and let them figure it out. Yeah. But it's a hard, they sit back too. We've sort of fallen in this trap of they're just saying, oh yeah, just give it to me, lay it on me, and give me the forecast. And we almost come back and say, well, we can't unless we know it is exactly what you need.
Yeah, I mean, I think yesterday we saw with Rob's presentation, it's the XLRM approach. So that tries to structure the decisions, the options, and everything in a far more exhaustive way than we clearly did here. The initial motivation for this interaction was to ask what can we learn together by trying to take a more holistic view. So we see the climate scenarios as not just temperature and precipitation. They link indirectly to these other behaviors, other responses in the system. And how can we design these narratives that are sensible, but then use that more holistic thinking to explore an adaptation option? And we happen to choose this one that I've tabled as essentially a proof of concept, a means of exploring the actual approach, the methodology, which is as much about the science industry interaction as it was about how you set up, calibrate, and run the models to explore an adaptation option.
Okay, I think we're going to take this discussion into the coffee break, by the sounds of it. Thanks to Rob again. And we'll come